Oh, in my last video, I've talked about how to make sense of determining how many points there are in a set when the set's infinite. And we explored the world of transfinite cardinals. If you haven't watched that video, you might want to do that because I'm going to draw on some of those ideas for this one. But in this video, I'm going to talk about a completely different way of making sense of infinity, which relies not just on how many points there are in a set, but what order they come in. So there we are, that's my title. And let's start with some examples so you can see what I'm talking about. Here's an infinite set. Well, it's not infinite, is it? Because it goes off the edge of the page. But I'm imagining that it does go on forever. And it sort of, you could label it, couldn't you? 0, 1, 2, 3, blah, 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 forever. In terms of our last video, that's an accountable set. There are A left null points there in a line. It's not the only way to arrange A left null points in a line. How about this one? Um, well, I'm going to say that's really the same arrangement. So I'm imagining here there are infinitely many, but they're scrunching up one another, a bit like the points on the number lines, or a 0.9, 0.99, 0.999, and so on. So there are infinitely many, and they're in a line, and it's really the same arrangement as that. Now, what do I mean by really the same arrangement? What I mean is that you can line them up in order and tick and mark them off. So that goes with that, that goes with that, that goes with that, that goes with that, and so on all the way along forever. But that's not the only way you can arrange A left null points in a line. Here's another one. Now this is different. This one has a last element, whereas this one doesn't. So in particular, you can't really line them up from the beginning because you do this and you run out at this point. There's nothing for this to line up with. So it's definitely a different arrangement. And in some sense, it's a bigger arrangement, or it's got the same number of points. So what happens here, the new guest arriving at Hilbert's hotel, instead of the hotelier shuffling all the guests up one and putting in room zero, he just builds a new room at the end. So it's definitely a different arrangement. Of course, we can also have finite sets arranged like that. And this sort of thing can't happen with finite sets. You can't sort of rearrange these six dots and make it look any different. It always looks like six dots in a line. Whereas here, this looks like infinitely many dots in a line, and this looks like infinitely many dots in a line, and another one. Right, so these are called ordinals, and they're well-ordered sets. I'll tell you what well-ordered means in a moment. They've got names. So this one's called omega. And so this one, which is just the same, is also called omega. That one's called omega plus 1. As you can see, it's sort of a sensible enough name, isn't it? It's omega and then another one. And this one, of course, is called 6. The points are all arranged in a line. So for any 2 points, one of them's always to the left of the other. They're not sort of scattered around all over the place. And the other defining characteristic is that however far you get along the line, there's always the next one. So that's true here. However far you get, there's always the next one. Here it's true as well. There's always the next one. And once you've done all those, there's still the next one. Okay, let's look at some more examples. That's omega plus 4, a fairly obvious idea. This one's, you do the whole thing twice. You get omega then omega, which is omega plus omega or omega times 2. And get more complicated. How about this one? Omega times 3 plus 5. So that, whoops. So that's omega, 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 and then 5. And these are all definitely different, aren't you? You can't line them up so they're the same. Here's an even bigger one. This is omega times omega. So we do omega, omega, omega forever. And you can get bigger ones still. Right. Now, to get a firmer idea of what this well-ordered thing means, let's go back and look at some examples of sets that are not well-ordered. So this is the simplest example. This is like omega backwards, and it doesn't start. There's no start. So there's always got to be a next one, even before you started, which means there's always got to be a first one, and there isn't in this case. So that's definitely not well ordered. This is the worst example. Supposing you have on the number line, you put down a half, then a quarter and 3/4, an eighth, 3/8, 5/8, and 7/8, and all the 16ths, and so on. And have the whole lot, infinitely many. Well, they're all in a line, but as well as there not being a start, after each dot, there isn't a next one. Suppose you had a half. What comes next? Well, there isn't one. So those are definitely not well ordered. So going back to these are all well ordered. There's always a next one. Now then, here's another thing that we can do with well-ordered sets. Take any two well-ordered sets. Here I happen to have chosen, what is it, omega plus 4 and omega times 3. And we can line them up. until we run out. So they have a start. They can do that. Then there's a next one, and then there's a next one. So we can line those up, the next one. And when we've done all that, there's the next one, and the next one, and so on, until we run out on one or the other. So given any two ordinals, it's always true that one of them is bigger than the other, and that, well, unless they're the same, one is always bigger than the other, and the smaller one is an initial segment of the bigger one. So it's the start of the big one, and that's always true for any two ordinals. And that means, in a sense, it's a sort of standard order of the dots, and we can label them. So, well, it's obviously how you start, isn't it? It's 0, 1, 2, 3, blah, 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 all those. And what would we call the next one? Well, omega seems to be the obvious answer, and then omega plus 1, and so on. And what's going on here? So previously, we've used a symbol like omega to mean a well-ordered set, and it's this well-ordered set. Now we're using it to mean a point in a well-ordered set. So that this omega refers both to this point and to the well-ordered set to its left. So that's omega, and that point's omega. That point's omega plus 1, and that well-ordered set is omega plus 1. That point is 2, and this well-ordered set is 2. That point is 1, that well-ordered set is 1. And that point is 0 because the well-ordered set to the left of it's nothing at all. That's why we start counting from 0, by the way. Okay, right. Back to our main example. So some of these ordinals have a last member, a last element, and some don't. So these two do, and that one does, but that one doesn't, that one doesn't, and that one doesn't. So one that doesn't have a last element is called a limit ordinal. So that's omega in this example, omega times 2, and this one is omega times omega. And you may notice, well, you can have a finite ordinal, but if it's transfinite, then it always consists of a limit ordinal plus a finite ordinal. So this, for example, this omega times 3 is omega times 3 there is a limit ordinal, and then there are 5 more. Okay, now there's one more important characteristic here of well-ordered sets. We'll use this as an example. Suppose we choose a subset of all those points, any old subset. So I've painted them red. I've just chosen a few of those, all of those, and a couple of those. So it doesn't matter whether it's an infinite set or a finite set. I've just chosen some set. And what I assert is that when it's well ordered, there's always a leftmost red point, a leftmost one of this subset. Well, there is here, and there's that one. But can we see that always would be whatever set we choose? Well, well, of course, if the red dots go right back to the beginning, then of course there's a leftmost red dot because it'll be this one. If it doesn't, then there are some green dots to the left of all the red dots. So let's take all the green dots that are to the left of all the red dots. Well, it's got to be a next one. Well, it must be red, and it must be the first red one. So that's it. Any subset has a first element. Now, what that means is we can now show that any ordinal is a limit ordinal plus a finite number. It certainly looks like that. This is omega plus 4, omega times 3 plus 5. So how can we show that? Well, if it hasn't, take any old transfinite ordinal. If it hasn't got a last element, then it's a limit ordinal, we're done. If it has got a last element, let's take that, put that aside, hold it in our hand, and look back before that. Well, if there isn't now a last one, then we're in this situation. It's an ordinal plus 1. Otherwise, we keep going. We keep taking them off and putting in our hand until we hit a limit ordinal, or maybe we don't. What goes on as we keep on taking them off? Well, we can't take off infinitely many, because if we did, this subset that we've taken off wouldn't have a first element. It would look like that omega backwards thing, and we can't have that because that would not be well ordered. So in other words, if there's a last one, you can take it away, but you can only do that finitely many times before you hit a limit ordinal. So every ordinal is a limit ordinal plus a finite number. Right, so let's summarize all that. So what we're saying is that an ordinal number corresponds to a well-ordered set. That's one where they're all in a line, and this defining characteristic, there's always a next one until you run out. And we show that given any two ordinals, one is always an initial segment of the other. They can be finite or transfinite. I didn't really mention this on the way through, but all those ordinals we looked at were countable. They've got A left null points. That last one, for example, which was omega squared, that's the case of infinitely many infinite coach parties arriving, isn't it? And still only countably many of them. They still fit in the hotel. There are, so all those ordinals are countable. You can have uncountable ordinals as well, but they're much harder to imagine and impossible to draw. So we're not worried about those. So some ordinals do not have a last member, and they're called limit ordinals. Every subset has a least element. And from that, we could show that every transfinite ordinal is a limit ordinal plus a finite ordinal. And an ordinal name applies both to an order type, that's an arrangement of a well-ordered set, if you like, and to the dot that comes next in a slightly larger well-ordered set. Okay, so we've called these things numbers. Well, are they? Can we do anything with these numbers? Can we add them up? Well, yes, we can. And here's how we do it. So what we mean by alpha plus beta is going to be we put alpha down and then we lay beta to its right. So that whole thing is a well-ordered set. Well, is it? Yes. So it's got a start because alpha's got a start. If you're trundling through alpha, there's always a next one. When you've finished alpha, there's a next one because it's the start of beta. And then as you trundle through beta, there's always a next one. So yes, alpha plus beta is a well-ordered set. Let's look at some examples. So here's omega. And here's omega plus 1. We've met that before, haven't we? But now we know that is the right name for it because that really is omega plus 1. What about 1 plus omega, though? So 1 plus omega, that's just omega, isn't it? Because we can line it up with omega. We can do that, and all the way, that, and so on, all the way along, and it lines up perfectly. So that is just omega. Here's a more complicated example. So this is omega plus 1 plus omega plus 2. Well, this 1 and this omega in the middle, look, this omega just gobbles up that 1, like this one did, like that one gobbled up that one. So this is really just omega, omega 2. So omega plus 1 plus omega plus 2 is omega times 2 plus 2, which is rather odd, isn't it? So we're seeing that an ordinal addition is a bit odd, in that it's certainly not commutative. But let's see what its properties are. So alpha plus beta means alpha then beta. And that means what you'd expect if alpha and beta are both finite. So 3 plus 7 is 10, and so is 10 plus 3. But otherwise, if either of them is infinite, then is transfinite, then alpha plus beta is not necessarily equal to beta plus alpha. They are associative, though, because alpha plus beta plus gamma is the same as alpha plus beta plus gamma, because they're both just alpha then beta then gamma. What else can we say? Well, if you add 0 to an ordinal, it stays the same. Obviously, if you put nothing to the left of it or nothing to the right of it, it doesn't make any difference. On the other hand, if you take something bigger than 0, if you add it to the right of alpha, then alpha definitely gets bigger. But if you add it to the left, it doesn't necessarily get bigger. It can't get smaller, though. Okay, so what about multiplication? So alpha times beta means beta lots of alpha. So remember, this is a probably transfinite ordinal, and under each dot, there's this alpha, which may also be a transfinite ordinal. So it can be a pretty humongous thing. Now, I don't know what your mental image of 3 times 7 is, whether it means 7 lots of 3 or 3 lots of 7 to you. Of course, with finite numbers, it doesn't matter. But with transfinite ordinals, it does. And alpha times beta always means beta lots of alpha. Okay, so let's look at some examples of that. So here's omega. And here's omega times 3. So that's just 3 lots of omega. Boom, boom, boom. There we go. So we've met that before. We've met that one before, haven't we? Now, what about 3 times omega? Well, that's omega lots of 3. So we just have this arrangement of 3 logs. Well, that's just omega again, isn't it? Because you can line it up, that one, that one, that one, that one, that one, and so on. So that's just omega. So again, multiplication is not commutative. Let's summarize where we've got to on that. So alpha times beta means beta lots of alpha. It means what you'd expect it to mean if alpha and beta are finite again. So 3 times 7 is 21, and so is 7 times 3. But otherwise, alpha times beta is not necessarily equal to beta times alpha. But again, it is associative. So it behaves like finite numbers to that extent. So um, this is gamma lots of beta lots of alpha, and that's gamma lots of beta lots of alpha, and they are the same if you pause and think about it a bit. If you multiply by zero to the left or the right, you get zero. So however many zeros you have, it's still zero. If you only have zero copies of anything, you have zero. Similarly, 1 times alpha and alpha times 1 is just alpha. So alpha times 1 is alpha lots of 1 dots, so that is just alpha. And 1 times alpha is just 1 alpha. So yeah, it is. So if beta is bigger than 1, if you multiply alpha by beta on the right, it definitely gets bigger. But if you multiply it on the left, it doesn't necessarily get bigger. But again, it can't get smaller. One other thing, alpha addition and multiplication come together. Um, well, so this distributive law holds alpha times beta plus gamma is alpha times beta plus alpha times gamma because this is beta lots of alpha and then gamma lots of alpha, and they're both that. But this is not necessarily true. In fact, we already met this one because omega plus 1 times 2 is omega plus 1 plus omega plus 1, which is really just omega plus omega plus 1. In other words, ordinal arithmetic is left distributive, but not right distributive. Okay, now you may remember that I started all this because my granddaughter asked me a tricky question. Grandpa, she said, is infinity even or odd? So now is the time to answer that question for ordinals. When we looked at it for cardinals, it was a bit dull because it turns out all cardinals are even. That's the end of the matter. All transfinite cardinals. Now, with ordinal, it's definitely going to be more difficult, isn't it? Because, well, there are two meanings for even. We could mean 2 times something, or we could mean something times 2. Well, we better do both, hadn't we? So let's start with 2 times something. So any something, any transfinite cardinal is a limit ordinal plus a finite ordinal. Now, in this case, I've chosen to illustrate this limit ordinal is only times 2, and the finite ordinal is 5. So when we do 2 times that ordinal, we just replace all the 1 dots by 2 dots. So that doesn't make any difference to the limit ordinal. We've seen that 2 times omega is omega. In fact, 2 times any limit ordinal is just the same thing. So that stayed the same. And of course, the finite bit's doubled. It's different now. So what that tells us is that a transfinite ordinal is even in this sense exactly when the finite bit's even, whatever the limit ordinal looks like. It's even if the finite bit's even, and it's odd if the finite bit's odd. If you do 1 plus an even ordinal, it's still even. 1 plus an odd one is still odd. But if you add 1 to the right, then it definitely changes an odd one to an even one, and an even one to the odd one. So an even ordinal plus 1 is odd, and an odd ordinal plus 1 is even. Okay, now what about something times 2? So this time I've chosen to illustrate with just omega plus 5 as our general ordinal. So that's the limit bit and that's the finite bit. So when we do that times 2, we just copy it out twice. And now this finite bit gets gobbled up by this limit bit in the way we've seen over and over again. So this is just limit bit times 2 plus 1 copy of the finite bit. So now it doesn't matter whether this finite bit is even or odd. This number is even if the limit bit's even, whether the finite bit's even or odd. And that means that whether you add 1 to an even number to the left or the right, it doesn't make any difference. And similarly, if a number like this is odd, then if you add 1 to the left of it, it's still odd. And if you add 1 to the right of it, it's still odd. So there we are. There's masses more we could say about transfinite ordinals. It's a fascinating subject, but that's enough for one day.